Welcome to the demonstration of MediAssist, our AI-driven patient health history chatbot with advanced clinical capabilities. In this video, we'll walk you through the key features, technical architecture, a live demo, RAG and fine-tuning results, and the lessons we learned along the way. MediAssist is designed to transform how clinicians interact with patient data. Our key features include patient history summarization. It allows you to automatically compile a patient's healthcare journey, making it easier for clinicians to review. Medical coding automation. It assigns standardized ICD codes for diagnosis and procedures from clinical notes. Patient risk stratification. It identifies high-risk patients to prioritize care. And finally, retrieval-augmented generation module. This offers precise and context-aware answers for complex clinical queries. A chatbot bridges the gap between raw clinical data and actionable insights, optimizing clinical workflows. MediAssist operates on a robust multi-layered architecture. First, the data sources. We use the MIMIC4 dataset featuring clinical records, diagnosis, and medications. Secondly, the data is passed into tools like Alteryx and Snowflake which streamline ETL and schema inference, ensuring efficient data handling. This is the stage of data ingestion. Next comes data transformation. With dbt, we clean and standardize data to support analysis and model training. Finally, data is stored in fact and dimension tables which are organized into optimized schemas for specific applications. This data is stored in Snowflake database. Finally, the application layers. Models such as Llama 3.2 and our own fine-tuned GPT-4o model powers patient history summarization, medical coding, and risk stratification. This architecture ensures high performance, scalability, and precision in healthcare analytics. Let's explore the chatbot in action. The first feature is patient history summarization. The chatbot analyzes data from multiple sources, including admissions, pharmacy, and discharge tables, to create a concise summary of the patient's healthcare journey using Llama 3.2 model. The user is supposed to click on search button after inputting the patient ID that they want to search. The system gives them information divided by their hospital admissions. Inside that, you can observe the admit date, discharge date, insurance, pharmacy details, and the neatly structured medical notes summary for that respective hospital admission. Also, the user is able to download all this information in a neatly designed patient report. Next, we demonstrate medical coding automation. The chatbot processes discharge notes and clinical data to assign appropriate ICD codes using the Llama 3.2 model. On this screen, user can search by patient ID or search by ICD code. If the user decides to search by patient ID, the user will get all the ICD codes associated to that patient across the hospital admissions. If the user decides to search by ICD code, the user will get a list of all the patients and the hospital admissions during which the patient faced this particular ICD code. What this ultimately helps doing is that it achieves highly accurate code assignments, streamlining billing and reporting workflows. The risk stratification feature categorizes patients based on clinical history and comorbidities to prioritize high-risk cases. On this screen, we have a dashboard which shows patient count by risk level along with trend of risk levels over time. We also have a section for patient details. On this screen, we have defined a certain risk stratification criteria ranging from level 1 to level 6. Based on this criteria, each patient is defined a specific risk level. To feature the risk level for a particular patient, you are supposed to search the patient based on the patient ID and click on the search button. When you click on search button, the system starts generating individual risk levels along with a justification which is generated via AI to justify how this patient risk has been allotted to that particular patient. Finally, we demonstrate the RAG module which retrieves and synthesizes detailed context-aware responses from extensive datasets. On the screen, the user is supposed to select the patient ID and its respective hospital admission ID. Based on this information, The patient's medical note has been fetched and it gets passed as a knowledge base for this chatbot. So let's click on process and start this chatbot. So I'll start by saying hi, and the chatbot will receive that information and provide a response in a streaming format. Now let's go with an example of generating a detailed report in 100 words. And based on that patient's information, the bot provided us with a much detailed information report. So, by leveraging fine-tuned GPT-4o model and vector embeddings, MediAssist delivers precise answers, aiding complex decision making. The reason that we decided to go with a fine-tuned model for this functionality is that the responses that we received from the bot were in a much tailored manner. To achieve optimal performance, we fine-tuned the GPT-4o model for 10 epochs using MIMIC4 data. Here's a detailed breakdown of the key observations that we observed. Training accuracy improved steadily, reaching 79.92% by the 10th epoch, demonstrating effective learning across the model. Regarding validation metrics, mean token accuracy rose to 83.45%, confirming better generalization to unseen data. Training loss declined consistently from 3.07 to 0.92, showing the model's enhanced ability to minimize errors. This progress highlights the success of fine-tuning efforts, particularly for tasks requiring precise understanding and retrieval in clinical context. The steady improvements in both training and validation metrics underline the GPT-4o model's ability to adapt to healthcare-specific tasks, making it a reliable tool for clinical decision support. Throughout the development process, we faced some key challenges and learned valuable lessons. First of all, data quality matters. Handling missing and unstructured clinical data required innovative pre-processing techniques. Secondly, scalable architecture. Optimizing Snowflake workflows was important to ensure seamless task orchestration. Thirdly, iterative model improvement. Regular clinician feedback was crucial for refining our models and enhancing usability. Next is integration complexity. Resolving schema mismatches and memory constraints in large datasets demanded adaptive solutions. And finally, each challenge strengthened MediAssist's capability to address real-world clinical needs. So, thank you for joining this demonstration of MediAssist. We are excited about the potential of AI in healthcare and look forward to your feedback. Together, let's shape the future of clinical decision making.